watching it afterwards. Usually it's not so crowded after the second, third week of class, so if this is your first class at Berkeley, if you're a grad student or something like that, don't worry, it's not always like this. It's just the first lecture and maybe the second and third lecture. And we'll begin in 4 minutes because last time I tried to start before Berkeley time, people got unhappy at me. So we'll start at 10 minutes after sharp. The what? Yeah, I'll cover the enrollment policy in the lecture slides. And then if you have a specific enrollment question, you can ask me after class. Okay, so here's how it's going to work. There's a screen outside, and apparently they're going to show the lecture on that screen. So at this point, I don't think anybody else can plausibly get in. So when people are kind of crowding at the door like that, and they're unhappy that they can't see the lecture, you can tell them that they can watch the screen. It's also webcast, and there's a link on the course website, so it's going to be live, and they can just watch it on their laptop. And then their third option is to watch it afterwards, watch the recording on YouTube. So just make sure that they know that they can watch the lecture either outside, on their laptop, or afterwards. Okay, thanks. All right, everybody, we're going to begin. So as I mentioned before, the room is full, as you've probably noticed. The lecture will apparently be shown on the screen outside the room as well. So if you're kind of at the entrance and you can't quite get in, you can't see, you can watch it on the screen outside. It's also webcast live, so there's a link on the course website. So if you Google Berkeley DeepRL, you can find the course website, go to the link and also watch it online if you can't get into the room. And it's also recorded, and you will be able to watch it afterwards. And for those of you that are presently watching this online, welcome to the class. For the rest of you, also welcome to the class. This class used to be called CS285 Fa19, Deep Reinforcement Learning. This year, for the first time, it has a permanent course number, CS285. So hopefully you're all here for CS285. And the course is now called Deep Reinforcement Learning, Decision Making and Control, because we do cover a variety of topics, not just core RL algorithms. Okay, so I'll begin with a little bit of logistics, a little bit of introductions, and then for the first lecture, I'll kind of set up what it is that DeepRL actually deals with and maybe motivate a little bit why we should study DeepRL. But let's start with the logistics. My name is Sergey Levin. I'm an assistant professor here at UC Berkeley in the Electrical Engineering and Computer Sciences department. I work on machine learning, robotics, deep learning, and of course reinforcement learning. We have four wonderful GSIs this semester with us. Frederick Ebert, who will be the head GSI. He's done some really excellent work studying model-based reinforcement learning, robotic control, and so forth. Anusha Nagabandi, she's also done a lot of work on model-based RL and robotics. A really wonderful person to talk to also if you're interested in robotics applications. Avi Singh, he's done a bit of computer vision, inverse RL, things like that. And Kelvin Xu, who's done some work on meta learning, reinforcement learning algorithms, and so forth. And Kelvin is actually here today. I think he might be outside helping people figure out how to watch the lecture. So all of the TAs and myself will have office hours every week. You're welcome to come in and talk with us. For kind of homework project-related questions, you'll probably get slightly better mileage from talking to the GSIs, especially if you can figure out which of them actually made the homework. But you're also welcome to come talk to me about that. If you have conceptual questions, definitely come in and talk to any of us about that. If you have questions about your final project, which is a more research-oriented project, definitely feel free to come into office hours, discuss ideas. We're always happy to talk about that. The course website, here's the course website. This is very important. This is going to be your primary resource for all things related to the course. We'll post lecture slides there. We'll post homeworks there. If you want to find the link to the YouTube lecture recordings, that's also on the course website. And there's also a link there to previous offerings of the course. So if you want to see slides, homeworks, and videos from previous years, you're also welcome to go and check those out. We're going to be using Piazza for communication for the course. Those of you that are enrolled in the course should have automatically been added to the Piazza, but if you haven't, it's UC Berkeley CS285. If you're having any trouble with Piazza, just go ahead and contact the TAs. If you're not sure who to contact, just start with Frederick and he'll be able to direct your questions appropriately. We'll be using Gradescope for assignment submissions and grading. So this is not urgent, but when it comes time to hand in homework 1, make sure that you are signed up for Gradescope. Again, all enrolled students should have been added to Gradescope automatically. For those of you that are watching the course online, if you are not an enrolled student, not a UC Berkeley student, we also have a subreddit. So you are welcome to go and discuss course material there if you're following along online, and there's a pretty healthy community there, and I'm sure that there'll be some folks who will be happy to answer your questions. And then the office hours are posted on the course website. My own office hours will be on Wednesdays immediately after class, 11:30 to 12:30. Currently, they're, I believe, upstairs in SOTA 734, but they might change because I'm trying to get a room that's a little closer to the classroom on the 3rd or 4th floor. Okay, prerequisites and enrollment. So this is a graduate level course. We do assume that you have substantial familiarity with machine learning topics. We don't teach basic machine learning in this course. We also don't teach basic deep learning. So we assume that you have met the prerequisite, which is a college-level machine learning course. So if you're a UC Berkeley student, this would be something like CS189, CS289, or CS281A, or an equivalent course at your home institution. If you're not sure whether you meet the prereq, or you're not sure if the particular course you've taken in the past actually covers the material that we assume you know, please feel free to get in touch with me. You can stop by office hours, or you can just send me an email. If you're sending me an email about a past course, good idea to attach the syllabus to that email. So the course is currently set up so that graduate students in EECS can enroll. If you are not eligible to enroll directly into the course, we will have some number of spots in the class available for undergraduates, for fifth-year master's students, PhD students from other departments, and so on. We may not be able to enroll everybody. Please make sure to fill out the enrollment application form on the course website. So this is the mechanism that we will use to determine who to enroll in the course. We do not use the official Cal Central waitlist because we can't ask questions about prerequisites and things like that via that waitlist. So please make sure if you want to be enrolled in the course and you cannot enroll directly through Cal Central, fill out that form. We will go through that form probably this Friday or this weekend, and then we will send enrollment codes to people who are at the top of the list. It doesn't matter what order you fill out the form in, whether you did it 3 months ago or today. We're going to randomize it and sort by priority based on whether you meet the prereqs or not. But please make sure to do this before Friday. And we'll not use the official Cal Central waitlist. If you're already enrolled via Cal Central, then you're fine. Don't worry about it. Okay, so lectures are recorded and live streamed. There's a link on the course website, so you're very welcome to come to class. If you can't make it to class, feel free to watch them online. The lecture room is obviously very crowded today. from past experience, it doesn't stay this way. So by the third or fourth week, there's going to be like, half the seats will be empty. So if you want to come to class, feel free to come to class. It's not always going to be like this. And I encourage you to come to class so that you can ask questions and engage with the material. But I understand that 10 a.m. is a little early for some folks, and you're welcome to watch it online. All right, what you should know. So definitely you should make sure that you have the prereq, that you've taken a college-level machine learning course before. We do assume a little bit beyond that. We do assume that you actually have some familiarity with deep learning at the level of being able to train a deep neural network. We're going to be using TensorFlow for all of our assignments in the course. So you do need to make sure that you're familiar with TensorFlow. For those of you that are not familiar with it, we will have a review session on Monday in week 3 on September 9th. Kelvin will lead the review session, and we'll have some materials for you. But if you want to get an understanding for whether kind of your proficiency with TensorFlow is sufficient, check out the low-level intro at this link. And if you can follow along with that and everything just works out and you can train your MNIST classifier to get 99-point-something% accuracy, then you're probably in good shape. But if you try going through it and it's really kind of a pain and not really working out, then you should definitely attend Kelvin's review session. This is going to be the third lecture in the class. So in the second lecture, I'll present material and imitation learning. The first homework will come out. You can even give that a shot a little bit. And if it's kind of a struggle, then on Monday, week 3, you can come to Kelvin's review session and learn about TensorFlow. Okay, what will we cover in the course? So one good way to get an idea for what we cover in the course is to check out last year's offering. You can go through that. We'll cover fairly similar material. We do update it every year to make sure that we're up to date. DeepRL is a very fast-moving field, so I typically need to revise, a good third of my slides to basically remove the things that we've since discovered are false, add the things we've since discovered are true, and so on. But the high-level outline will be similar to last year, so you can check that out. Broadly speaking, we're going to start off with a discussion of how we can go from supervised learning methods to decision making, starting out with imitation learning, a little bit of theory about imitation learning, a little bit of practical algorithms, and then move into the fundamental model-free reinforcement learning methods, policy gradient methods, Q-learning, actor-critic algorithms. Then we're going to talk about model-based reinforcement learning, some advanced topics for model-based learning and prediction. We're going to cover more modern, sophisticated topics like transfer learning, multitask learning, and meta-learning towards the middle of the course, as well as algorithms for exploration. And then in the second half of the course, we're going to go to kind of more advanced researchy kind of topics where I'll give a few lectures on current research, current cutting-edge techniques, and we'll also have invited talks from researchers in the field that we'll invite to tell you about kind of their own ongoing work. So here is the list of lectures from last year. It won't be exactly the same as last year, but it'll be pretty similar. So you can see that basically kind of the first half of the course is core algorithms, policy gradient, actor-critic, etc. And then the second half is kind of the more advanced stuff, a little bit of variational inference, a little bit of inverse RL, things like this, some meta-learning, etc. Okay, we're going to have 5 homework assignments and a final project. So the homework assignments will mainly be concentrated towards the first half or 2/3 of the class to cover the core algorithms, imitation learning. You're going to have a homework on policy gradients, a homework on Q-learning and actor-critic methods, a homework on model-based RL, and then homework 5 will focus on some advanced topic. We haven't decided exactly what it will be, but it will be some kind of advanced model-free RL algorithm. And then the other major bit of work for you in this course is your final project. So for the final project, we expect a research level project, something, maybe for a scope of something you might submit to a workshop at a major conference, for example. You can form a group of 2 to 3 students for the final project. You're also welcome to work alone if you'd like. If you want a group of more than 3 people, please come and see me or one of the TAs to discuss what you want to do. We will, of course, adjust our expectations for the project based on the size of your group. It's also perfectly fine to work with students that are not enrolled in the class. So if you're working on research with another student who's not a student in this class and you want to work together on something that will be a final project in this class, that's generally okay. But if you're not sure, then come talk to us. We will expect to know what you actually contribute to the project yourself. Grading is pretty simple. Half the grade is your homework, half the grade is your project. Each of the homeworks counts for 10%, and your project counts for half of your grade. We do expect you to turn in your assignments on time in this class. So it's a larger class. We have to manage logistics somehow. So we will have deadlines for all these homeworks. You have to turn it in on time. You have a total of 5 late days for the entire semester. So that means that the cumulative number of days that all of your assignments are late needs to not exceed 5. If it does, then we unfortunately can't grade your homework. So please make sure to get in your homeworks on time. You have a little bit of homework for today, but I promise it's very, very easy. Sign up for Piazza if you're not already signed up. Start forming your final project groups, unless you want to work alone, which is fine too, but the final project does take a while, so if you start thinking about ideas and start thinking about who your group members will be today, then by the time we release the project proposal assignment, you'll already have some idea of what's going on. Review the TensorFlow low-level intro to make sure that you're really up to speed with TensorFlow, and if it's a little bit tough going, then consider attending the review session in week 3. And that's it. So long as you do these 3 things, that's enough for today. We will release the actual first homework next week. Okay, so that's course logistics. Does anybody have any questions about course logistics? Yes?
How do you sign up for Piazza again?
How do you sign up for Piazza? I believe you go to Piazza and then you look for CS285. But if you can't find it, then contact the TAs. Yes?
For the projects, do the school claims IP, this class claims IP, or the students can have it?
I have no idea because I'm not a lawyer. But you could contact, maybe like the registrar's office to try to find out. Yeah.
If we're taking 287, are we allowed to overlap the project scope at all, or no?
Yeah, so the question is, if you're taking 287, are you allowed to overlap the project scope? Yeah, I'm fine with that. Any other questions? Okay. All right, so let's talk about the core material for today's lecture. What is reinforcement learning and why should we care about it? So one of the reasons that I think we might care about it is because perhaps reinforcement learning actually is a really important ingredient for the question of how do we build intelligent machines. Maybe this is not something that all of you are concerned with, but it is something that I'm pretty concerned about. What do I mean by intelligent machines? Well, I kind of mean the obvious thing. Maybe you watched some cartoons as a kid. You saw robots that can do some pretty impressive things. You thought, well, maybe it would be really cool if we could have one of those. Maybe something a little bit more modern like that. Perhaps you're a science fiction fan. You want to know how we can build Lieutenant Commander Data, or maybe you have a slightly more nefarious mindset and you're more into things like this. But one way or another, there's this kind of impression that we get, partly from culture, from fictional stories, also from our own imagination, that if we could build intelligent machines, machines that exhibit the kind of intelligence that humans exhibit, that would be a really impressive thing, a really interesting thing, and also maybe something with very profound social implications, that this is something that would transform our society. So how can we go about doing that? Well, one of the things that we might think about first is, what is it that makes intelligent machines difficult to build? Clearly people have been trying for a long time and it's proven to be very difficult. There are certain kinds of intelligence that are actually relatively straightforward to get with current technology, and certain kinds of intelligence that are very difficult to get. So for example, if you have some really complicated mechanical thing, like let's say an oil tanker, it's a really big oil tanker. One might think that driving an oil tanker is a highly specialized skill. You maybe need to get some special training to do that. But it's actually pretty easy to design algorithms that can navigate an oil tanker around the world, using a little bit of GPS and a little bit of path planning. It's not actually a very difficult computational problem. But you typically do want some people on board that oil tanker. Why? Well, not because it's so hard to navigate, but because when something goes wrong in the engine room, something unexpected happens, you really need a person to go in there and fix it. So one of the things that makes human-like intelligence so challenging is that humans are not just smart, they're not just good at solving problems, but they're also highly adaptable. We can figure out how to respond to situations even when they're messy, unexpected, unpredictable, when things that maybe would have been difficult to program into a computer are required of us. So this guy can probably go into the engine room, figure out what actually happened. Maybe he doesn't know how to fix it, maybe he calls up his friend, but he's resourceful enough to figure that out. Another kind of resourcefulness, that kind of common sense, is actually the thing that turns out to be very difficult. So deep learning and reinforcement learning combined might provide us with perhaps a little bit of an idea about how to tackle these kind of problems, and here's why. Deep learning is one of the best tools that we have today for handling unstructured environments. So what is an unstructured environment? Well, an unstructured environment is something like this. It's an environment that was not designed for the machine to work well. A factory is a structured environment. The engine room of the oil tanker is an unstructured environment. So deep learning models, deep neural networks, are very good at handling unstructured environments because they can learn from large amounts of data, they can discover patterns, and they can process raw sensory inputs like image pixels. So you could build a deep network that will look at an image and tell you that, this is an image of, in this case, a tiger. And you can train that neural network on thousands of different image categories using data sets with millions of images and get things that can not only recognize tigers, but container ships, motor scooters, leopards, etc. Lots and lots of different things. You can build deep neural networks that can translate text, recognize speech, and so on. These are all raw, unstructured, real-world sensory signals that weren't designed for the machine to work. They're the kind of situations where typically humans excel and machines struggle. But none of these are really decision-making problems. These are really recognition problems, passive recognition problems. So reinforcement learning really provides the other half. It provides a formalism for behavior. It's not enough to just be able to process complex sensory signals. You also need a mathematical framework that allows you to formulate an objective that will result in the system actually making decisions. And that's what reinforcement learning provides. Reinforcement learning is essentially a mathematical formalization of a decision-making problem. In reinforcement learning, you have an agent and you have an environment. The agent interacts with the environment. The agent makes decisions, which we call actions. Sometimes we call them controls. And the environment responds with the consequences of those actions, which are observations or states, and rewards, also sometimes called costs. And reinforcement learning is basically about turning this picture into a mathematical formalism, something that we can actually start from to design meaningful algorithms. And reinforcement learning is a topic that's been studied for a very long time. It actually started out as a study of biological intelligence, but has really taken off in computer science. Reinforcement learning has been used for things like playing games. One of the earliest major successes of reinforcement learning was actually a system that could learn to play the game of backgammon at a level competitive with proficient human players. In fact, a system that many of you might be more familiar with, which is AlphaGo. It's a reinforcement learning system that could beat the world champion at Go, used concepts that were actually very similar at a high level to those behind TD Gammon, which was the backgammon playing robot from the mid-90s. This was from 1995. So, we've got a few decades between TD Gammon and AlphaGo, but similar high-level principles. Reinforcement learning can enable simulated robots to learn how to run. It can enable robots to learn basic manipulation skills, playing Atari games, and even doing kind of robotics tasks at scale. And there are also other applications that I'll discuss a little bit later in today's lecture. So what is DeepRL really, and what's kind of the big deal with it? Well, one way to think about the big idea behind DeepRL is to think about it by analogy to what happened in computer vision. So computer vision is a field that at this point has been basically completely transformed by deep learning. If you go back maybe, let's say at this point, about a decade, you'll see computer vision systems that work basically like this. They start out with images because that's how computers see the world. Images consist of pixels. And then you would take those image pixels and you would extract some features from those image pixels. And those features would be designed by hand. Typically, designing a good set of features was sort of one PhD thesis worth of work. So for example, you might extract a histogram of oriented gradients. Maybe you would also have some higher level features. You could perhaps compose those oriented gradients into like a deformable parts model. And then on top of that, you would have a little bit of learning, typically a linear learning problem that can be formulated as a convex optimization, which would actually use those higher level features to detect the thing that you care about, which in this case is maybe a person. If you look at how computer vision is done today, with deep learning, we have a model that directly reads in the image pixels and is then trained to output the right answer. Now inside of this model, there might still be different layers of representation. In fact, there actually are layers of representation. They're not quite the same as histogram of oriented gradients or deformable parts models, but still features that do pay attention to particular properties in the image. The big difference is that those features are not designed by hand, but instead are learned, and they're learned end-to-end, meaning that the features that the network acquires are informed by the overall objective of the task. And of course, if you train those features on a very broad and diverse task, like classifying the image in a data set, then you might get very general, very broadly applicable features without having to actually engineer them yourself. And this end-to-end training is one of the major advantages of current deep learning techniques. So that's a story for computer vision. What does the story look like for decision making and control? Well, if you look again at standard reinforcement learning, again going back about 10 years, you might see a picture that looks a little bit like the one at the top here. So maybe you're playing backgammon. Perhaps you need to figure out some features of backgammon that matter for playing backgammon. What would those features be? Well, if you're very good at playing backgammon, then you might know some things about it. I don't really know anything about backgammon, but I know something about chess, so I might say that, well, if you're playing chess, perhaps some of the features you might care about are, how many pawns do you have? Have you taken the other player's bishop or rook or something like that? Do you have a knight in the middle of the board? Because that's kind of a nice thing to have. So things that, from your knowledge of the task, seem like they're important things for the policy to keep track of. In general, these features are kind of hard to design. In fact, they're perhaps substantially harder to design than the visual features because, at some level, recognizing a bicycle and recognizing a school bus are kind of related tasks, and the same histogram of oriented feature or of oriented gradients feature might work well for both of them. But playing chess and playing backgammon are extremely unlikely to have features in common, so you probably have to design your features per each task that you want to solve, which can be very onerous. Maybe you need more higher level features. It's a little bit non-trivial to imagine what kind of features are useful for representing the optimal strategy versus representing the optimal value function, etc. So you might need to put a lot of thought into that. And then on top of those features, you would have some kind of function approximator, typically a very simple function approximator like a linear function, that you would use to actually map those features to actions. So as you might guess from this description, this is a fairly manual and fairly onerous process, and in practice it actually turned out to be a major limiting factor for the application of reinforcement learning to new domains, because for each domain you have to think of these features, and how well your system does depends crucially on the quality of those features. So while it's a learning algorithm, it was not by any means an automated learning process for any but the simplest problems. So the big advantage of deep reinforcement learning in this case is, just like over here, you now don't have to design these features by hand, and in fact the features are actually optimized end-to-end for the objective you actually care about, which for backgammon might be winning the game. And that turns out to be crucially important because now it makes this into an automated process. When it becomes an automated process, of course, it's easier to apply to a new task, but perhaps more importantly, the features you get might actually be substantially better than the best features you could have thought of yourself. Okay, so what does all this end-to-end learning actually mean for sequential decision making? Well, if you imagine the alternative to end-to-end learning for a decision-making system, it would typically be a decision-making system where you separate out the parts and you design them yourself. You would design the features. If you have a perception component to your problem, you would design the perception system. So if, for example, you have a robot that needs to, navigate the jungle, perhaps it should avoid the tiger, you need to build your tiger detector, and then separately on top of that tiger detector, build your policy, maybe with some features or maybe learn end-to-end to choose what to actually do in response to those percepts. And each of those parts needs to be built somehow. And you need to decide what abstraction you're going to use. What is the thing that you're going to perceive that is then sufficient for you to act on it? In some cases, this is relatively easy to do, but in some other cases, it can be very difficult. If you imagine, for example, designing an autonomous vehicle, well, maybe to start with, it may be kind of obvious. Your autonomous vehicle needs to know where other vehicles are. It needs to know where pedestrians are. But if you imagine driving a car yourself, maybe you're driving down Telegraph, for example. There's a lot of pedestrians around. You're probably using a lot of other sensory cues. You might look at a person and you might see, well, are they staring at the sidewalk in front of them, or are they looking at like the storefront behind them? If they're staring at the sidewalk, maybe they're going to cross. If they're not looking at it, they're looking somewhere else, maybe they're not going to cross. There's these very rich and complex sensory cues that you use that are relevant to the task that might not be apparent in a manually selected abstraction. So if you can learn your sensory motor loop end to end, if you can actually map the percepts directly to actions, then you can allow the model to discover for itself what are the valuable things to pay attention to in the image. So to make this a little more explicit, I can give an example in a robotics context. This is a pipeline for designing a robotic system that might be fairly familiar for those of you that took a robotics course. If you want a robot to do something, then you typically approach that problem first as an engineering problem. You design the individual modules that the robot needs to make a decision. So maybe the robot needs to look at some observations, maybe images. It needs to do some state estimation, figure out where things in the image are actually located. Maybe then it has some kind of modeling or prediction system. It has to figure out, well, okay, the cup is over here. If I tilt the cup, will the contents pour out or not? So there's some kind of model of the world. Then that model is used for planning. Then that plan is then passed to a low-level controller, and that low-level controller actually executes the skill in the world. And the trouble with this kind of pipelined approach is that you can have a failure at every point in this pipeline. So maybe if the state estimation doesn't localize the object correctly, then it doesn't matter how good of a model you have. You're not actually modeling the thing that's really happening in the world because your state estimation failed. Or maybe your model is not so good, in which case the result that the planner produces will not be a good plan because it's predicated on the wrong assumption about the world. So that's the trouble with pipelines, is that if you pick the abstraction between each module and you pick the wrong one, then the errors from those incorrect abstractions will actually accumulate over the course of the pipeline, and by the end you'll get a completely nonsensical answer. So you could imagine an alternative, which is an end-to-end trained robotic system. That end-to-end trained robotic system still has inside of its policy components that resemble the functionality of state estimators, planners, and so on, but they're trained end-to-end. So for this robot, this is an experiment that we did here at UC Berkeley about 5 years ago. You have a robot that is performing some manipulation tasks using camera images, and it has a deep neural network that represents its policy. So the images from the camera go in through to the bottom of the network, and then out the top, it outputs motor torques that are then passed to the robot's arm. But inside that network, it has some convolutional layers and some fully connected layers. So if you want to strain the analogy a little bit, you could almost imagine that the convolutional layers are like this robot's really tiny visual cortex, as a very crude analogy, of course. And maybe the stuff at the top is a very crude motor cortex. This is the bit that actually decides how to act. Of course, much smaller than would actually be necessary for something like an animal or a person, but maybe good enough for this robot if his sole job is to play with this little children's toy and put the little red shape into the hole. So the model might internally have functionality that resembles the parts that we're familiar with, but the whole thing is trained end-to-end, which means it can choose which part of the input to attend to in order to best accomplish the task. Okay, so let's dig a little bit more into the formalism that we use in reinforcement learning. I'll, of course, go into the math and the details a lot more in future lectures, but to provide kind of a high-level idea of what's going on here. As I mentioned before, in reinforcement learning, we have an agent that interacts with the world. That agent makes decisions that we call actions, and the world responds with consequences, which we might call observations or states, and rewards. So what are examples of this? Well, maybe you're training a dog. We actually have a fair bit of evidence that animals like dogs are doing something similar to reinforcement learning when they learn skills. That's not the only way they learn skills, but that's one of the models that seems to explain behavioral data pretty well. What are the dog's actions? Well, its actions, actually the same as any animal, are going to be movement of its muscles. That's the way that the dog affects the world. Its observations are what it gets from its senses: sight, smell, touch, whatever, sounds. And its reward is, well, in this case, maybe it's whatever you're doing to train the dog. Maybe you give it a little treat, and that's where it gets the reward. Similarly, if you have a robot and you want to train that robot to do something, its actions are its actuation commands. Its observations are going to be the readings from its sensors, like camera images. And its reward might be, for example, a measure of whether it's succeeding at a task. So if you want this guy to run as fast as possible, maybe the reward function that you would program in for that robot will be a scalar value that is larger if it's running faster and smaller if it's running slower. But of course, you don't have to think about dogs and robots. You could also think of decision-making systems that are kind of a little more abstract. You could imagine, for instance, an inventory management problem. Maybe you're in charge of Amazon and you have to schedule the delivery of goods to warehouses and homes. That can also be treated as a reinforcement learning problem, but a different one. So here your actions might be a little bit more complicated. Maybe it's what do you purchase or what do you ship to each warehouse. You might have an extremely large number of possible actions. Your observations might be the inventory levels in your different warehouses, or maybe they're the orders that the users place in your online store or something like that. And then your reward might be the profit that you make at the end. So you might say, well, choose how to modulate the what you purchase based on the observations of your inventory levels so that you maximize your profit. That is also a decision-making problem, and it can be cast into the same mathematical framework as the dog learning tricks or the robot learning how to run as fast as possible. And a big part of the power of reinforcement learning is that the same mathematical abstraction can be used to tackle a wide variety of problems like this. In fact, the reinforcement learning problem is, in a sense, the AI problem. Insofar as an AI system is something that perceives the world and acts rationally in the world, reinforcement learning is actually a formalization of that problem. And actually most problems that we consider AI problems can be framed as reinforcement learning problems, although it's not always useful to do that. So you could, for example, say that image classification is a reinforcement learning problem. The image classifier gets a reward of +1 if it gets the right label and 0 otherwise. And you can train an image classifier with reinforcement learning. I wouldn't recommend doing that because there are probably easier ways to do it, but the point is that pretty much any problem that you would regard as an AI problem can be cast as a reinforcement learning problem. And deep models are what's going to allow reinforcement learning algorithms to solve complex problems end to end. So the reinforcement learning is the algorithmic foundation, and deep models are the representations that can allow us to make that algorithmic foundation applicable to general problems. So what kind of problems can we try to solve with reinforcement learning? Well, there's quite a big variety. You could, for example, imagine some physically complex tasks that you could solve with deep RL. This is an example from about a year and a half ago at this point. So this is a simulated robotic hand that learned a wide variety of behaviors, trained end-to-end with deep RL. So it could pick up a hammer and hammer in a nail, open a door, things like that, while controlling all the fingers on the hand. You could also get some unexpected solutions. So this is an agent using Q-learning, which we'll learn about in this course, that's learning to play the game of breakout. So in breakout, you're supposed to control this paddle at the bottom to break the bricks. And what this policy discovered is that actually if it's really clever and it knocks the ball up top, it'll actually bounce around up here and break lots of bricks without the agent having to do a lot of work moving the paddle around. So you get these kind of cool emergent behaviors that maybe you didn't anticipate when you implemented the algorithm. We can use deep reinforcement learning in the real world. So this is an experiment where multiple robots actually collected data in the real world for a grasping task. So the robots are kind of grasping different objects using vision. They're picking things up day in and day out, trying to see what works and what doesn't work. And after all that training, they can figure out some interesting strategies where they can say, well, if I need to pick up this object, but there's other objects around it, I can push them aside, clear up the space so that I can reach in and have a clear grasp at an object. If I try to pick something up, maybe I succeed and I'm happy about it. If I try to pick something up and I fail, then maybe I can try again. So here you'll see the retrying in a second. So there it tries to go for the cylinder, doesn't quite get it, and it's like, okay, I didn't get it, let me just go in and try again, and maybe it'll work better the second time. So the nice thing about this kind of stuff is that since it's a data-driven process, the learning is largely autonomous, right? You run it for longer, you get a better policy. And of course, it's not just about video games and robots. This is a question that I sometimes get in the course. It so happens that a lot of the research in deep reinforcement learning focuses on video games because it's easy to experiment with video games, and robots are also kind of a natural application area. But there are also other places that we can apply deep reinforcement learning algorithms that can be pretty exciting. So what I'm going to show next is actually work that was done by a former PhD student at UC Berkeley named Kathy Wu, who's now starting as a professor at MIT. And what Kathy Wu worked on was deep reinforcement learning for traffic. So here's a little toy example. This is I'll just explain what's going on here. So it is kind of an example of a simulation that can exhibit the world's worst traffic jam. So you have a bunch of cars that are going in a circle. And this red car over here is a car that is autonomous. So initially, it'll be executing kind of a selfish, greedy policy where it's just trying to be like everybody else, just try to drive as fast as it can. But then at one point, you'll see that it will actually switch to a different strategy where it will instead try to optimize the overall flow of traffic for all the cars. So it'll actually slow down or speed up so that everybody goes faster in the circle. So here's what happens. Initially, when everyone is being selfish, the cars kind of pile up and you get this little traffic jam emerging in the circle. But then after a while, this red car is going to decide that, yeah, so see how they're braking here, they're slowing down, forming a traffic jam. But now what it's going to decide is it's going to actually adjust how it drives to minimize traffic jams. So it actually intentionally slowed down to get all these guys to kind of space out a little bit, and now it's going to drive in such a way as to keep traffic flowing optimally. This is maybe a little bit more obvious in a different example. So here's a figure 8-shaped road, and you kind of can guess what happens when people arrive at this four-way intersection. They're going to have to wait for someone else to drive across, and that'll cause a little bit of a traffic jam. So here's what happens in the four-way intersection. So without any autonomous cars, you can see that they're kind of piling up here at this four-way intersection. and that's causing a bit of a traffic jam. But now if we switch to the autonomous case, so this is the autonomous car over here, what is it going to do? Well, it's going to just sit there and wait. What is it waiting for? Well, it's waiting to make this perfect line so that the line of traffic is exactly the length of 1/2 of the figure 8, so that everybody goes to the four-way intersection perfectly. And this is maybe a little bit of a contrived example, but you could imagine taking this idea and scaling it up further, where you might have many such cars that are modulating traffic to keep everything moving smoothly. Okay, so that maybe gives you a little bit of an idea of what are some of the cool things we can do with deep RL. Why should we study this now? Why is now a good time to look at deep reinforcement learning? Well, there are kind of three factors that I think are coming together very nicely in the last maybe 3 or 4 years that make it a great time to study deep RL. One, of course, is advances in deep learning, meaning advances in neural network architectures, techniques for training them, and so on, that make it actually practical for us to train big neural nets that directly read in complex observations, like the images that grasping robot needed to use, and output some non-trivial functions of those observations. The second one, of course, is advances in reinforcement learning. So reinforcement learning algorithms are fairly complicated. They're a bit more, substantially more complicated actually than supervised learning algorithms, which is why we need the first half of this course just to learn how the reinforcement learning algorithms work. And those have also come a long way. We've understood a little bit better how to design reinforcement learning algorithms that are convergent, that actually have favorable numerical properties, that are stable to use, that are reliable, and so on, although there's still a long way to go there. And then the third one is advances in computational capability. So computationally, it's actually quite costly both to train large neural networks and to use reinforcement learning methods. And that's something that has also come a long way. That said, a lot of the basic ideas behind deep reinforcement learning algorithms have actually been around for quite some time. So there are books, for example, on using neural networks for control going back to the 80s and 90s. This is an excerpt from a PhD thesis written in 1993 that actually has a few ideas that we would basically consider cutting-edge research topics today. For example, one of the things that this PhD thesis says is that reinforcement learning can be naturally integrated with artificial neural networks to obtain high-quality generalization. So that's obviously something that we're doing a lot of these days. It says that experience replay is a simple technique that implements this idea and is shown to be effective in reducing the number of action executions required. We'll actually study experience replay in this course when we talk about Q-learning, and we'll discuss how it's actually a really important component in getting practical Q-learning algorithms that really work. Instructive training instances provided by human teachers can result in significant learning speedup. So we'll talk a lot in this course actually about imitation learning and also other ways that we can incorporate human-provided demonstrations into the learning process. And that turns out to be a really effective tool, especially for the more complex behaviors. Reinforcement learning agents can significantly reduce learning time by hierarchical learning. Hierarchical reinforcement learning is also a very active area of research today. We'll probably have a little bit of discussion of hierarchical reinforcement learning towards the end of the course. Reinforcement learning agents can deal with a wide range of non-Markovian environments by having a memory of their past. We'll actually discuss recurrent neural networks, memory, and other related topics, particularly when we talk about meta-learning later on in the course today. So this is from quite a long time ago, but actually many of the ideas are things that we're still iterating on today. And then, of course, reinforcement learning methods have not only been things that people wrote about a long time ago, but they're also things that have actually worked quite well, even as early back as 1995. So I mentioned the TD Gammon, which was a system for playing backgammon. So if you're interested in learning more about that, there's a paper by Jerry Tesoro from 1995 that describes that. Okay, but in terms of things that are really coming together these days, we've seen some pretty impressive successes in the world of deep reinforcement learning that I think are cause for optimism in terms of how the confluence of these ideas today can enable some really impressive applications and also potential for really fundamental developments in technology, including things like RL systems that can learn to play Atari games, RL systems that can learn to control real-world robots, and of course, RL systems that can learn to play board games at a proficiency that often exceeds the very best human players. Okay, but reinforcement learning algorithms aren't actually the only thing that we're going to cover in this course. The entire decision-making and control problem actually goes beyond just core algorithms for reinforcement learning and touches on a number of other important questions. So what are other problems that we need to solve to enable real-world sequential decision-making beyond just core RL algorithms? And there are actually quite a few. So one question that actually often comes up when we go to use reinforcement learning in real-world settings is the following, that in reinforcement learning, you have agents that maximize a reward. So, if you're training the dog, you're training the dog by giving it treats. What the dog is trying to do is actually maximize its ability to get treats. Now, it doesn't necessarily care what you want it to do, all it wants is the treats. And a natural question to ask is, if you actually want an RL agent to do something useful for you, how do you decide what the reward function should be, and where do you get that reward function? It turns out to be a surprisingly subtle problem. So basic reinforcement learning deals with maximizing rewards. It's not the only problem in sequential decision making. We'll cover more advanced topics. So one topic we'll cover is learning reward functions from examples. I'll discuss this very briefly today as well. Transferring knowledge between domains, transfer learning, meta learning, and so forth, which can allow you, for example, to take a policy that was learned in some simpler setting and get some kind of knowledge out of that policy that can be used perhaps to learn a more complex skill. And then also learning to predict and using prediction to act. So we often draw a distinction between model-free reinforcement learning and model-based reinforcement learning. Model-free reinforcement learning refers to a learning setting where we don't try to understand how the world works, we just try to figure out how to get the most treats. Model-based reinforcement learning refers to a setting where we first try to figure out how the world works, understand physics, basically understand how to predict what's going to happen next, and then use that predictive mechanism to act. So let's talk about rewards first. Where do the rewards come from? Well, if you're playing Atari games, it's actually pretty obvious where the rewards come from. They're often written right there on the screen. So you want to maximize a score, there's your score, make that number big. In fact, games are kind of designed that way. In a game, it's pretty obvious who wins or who loses. In real life, it's not often quite that simple. So you could imagine, for example, a robot learning to pour a glass of water into a cup. This is something that any child could do quite well. But actually, if you imagine designing a reward function for this for a robot, the reward function itself actually requires a fairly sophisticated perception system. So just figuring out if you're pouring water from the jug into the cup, how much water is in there, you need to figure out the surface of the fluid, estimate volume, all this stuff. Doing that from images is actually kind of difficult. Perhaps actually more difficult than the policy that you need to tilt the jug and pour the water. So reward functions in the real world can be pretty complicated. And they can be pretty complicated for biological systems too. A few years back, a few colleagues of mine worked on a research project studying reinforcement learning algorithms that didn't require reward functions, and they posted their paper online, and there was some discussion about that paper on Reddit. And here's a comment that somebody made regarding that paper. This is actually a quote. So they're quoting the paper that says, "As human agents, we are accustomed to operating with rewards that are so sparse that we only experience them once or twice in a lifetime, if at all." And this person had a response to this. He says, "I pity the author." But there's some truth to that, right? If you try to learn how to, do well in college using reinforcement learning, you're probably going to go to college once in your life, not 20 times. And for each class, you're probably going to take that class once or at most twice. So it's kind of silly to imagine that you learn how to do well in class by trial and error. No, that's probably not what's happening. You actually have something quite a bit more detailed that's acting as your objective function. And of course, in biology, we also know that these things are quite a bit more complicated than the simple Atari game story might lead us to believe. So in fact, neuroscientists do actually have some idea of where the reward signal in the brain comes from. There's a piece of the brain that does it. It's this piece. It's the basal ganglia, most likely. And it's pretty complicated. So it's not just like some little switch that says yes or no. If you're eating food, it says +1, and if you're not, it says 0. It's actually a fairly complicated mechanism. And it makes sense that it should be a complicated mechanism, because if you imagine that you're like this cheetah chasing after the gazelle, if you got the reward only after you caught the gazelle, you'd have a pretty hard time actually learning how to hunt gazelles. If you're just randomly running around on the savannah, your chances of randomly cornering a gazelle and eating it are pretty low. So it makes sense that you would need some kind of more complex driving signal that actually leads you towards the meaningful behaviors that are actually useful for your survival. So are there other forms of supervision that we can think about exploiting for a reinforcement learning agent? Well, we can think about learning from demonstrations. So maybe that cheetah learned how to hunt gazelles by watching the older and more experienced cheetah hunt the gazelle successfully and said oh, that seems like a good idea. I should run after that thing with 4 legs because afterwards there's lots of meat. So you could imagine learning from demonstration by directly copying the observed behavior. Or you could imagine something more sophisticated, like using demonstrations to infer what that other agent was trying to do, and then accomplish that other agent's goals yourself, maybe using other means. You could learn from observing how the world works. So you could, for example, learn to predict. You can watch the gazelle and you can say that, well, when the gazelle is like really tired, then it's going to run much slower and then I can catch it easily. But if it's like morning and the gazelle just had his coffee, then maybe I'll have a lot of trouble catching him. You can do unsupervised learning, so you can observe the world around you, extract useful visual features from modeling the density of real-world observations, and then maybe that gives you good initial features. If you do your learning on top of those features, maybe you'll learn more quickly, and we'll actually discuss this idea towards the end of the course. And you can also learn from other tasks. So maybe the cheetah learned how to chase the gazelle, not by chasing actual gazelles, but by chasing some other slower animal. And then it said, well, animals in general are made of meat and they're tasty when I eat them, and these animals were easy to catch, so maybe I'll try chasing other animals now because I know that chasing animals is a good way to get meat, even if this other animal seems to be harder to catch. So you can do things like transfer learning, use experience from past tasks and transfer to new tasks to learn them more efficiently. You can do meta-learning, which is kind of one step beyond that, where you use past tasks not to learn facts about the world that are useful, but to actually learn something about the learning process itself. You can say, well, the way I figured out how to solve these puzzles was by trying these different things and then asking my friend and then doing this other thing. So when I'm faced with a new puzzle, I'll do those same things. I'll ask my friend, I'll do this other thing, and maybe then I can solve this new puzzle more quickly. So we'll cover many of these things. Let's talk a little bit about learning from demonstrations. This is an example that we'll discuss in more detail next week of an imitation learning system for driving a vehicle. So this is a machine that was trained to drive a car using lots of data of human drivers driving the car. It's doing some fairly reasonable things. We'll discuss next week whether this method is actually guaranteed to work or not, and in which cases it works and in which cases it fails. But high-level bit here is if you have lots of data of human drivers and you want to learn how to drive a car, seems like you should be able to leverage that data. But you can do more from demonstrations than just copy exactly what the demonstrator did. And in fact, people usually do a lot more from observing other people than just copy them. We actually infer their intentions and use those inferences to help us accomplish goals. So here's a video. This is actually from a study on child psychology. So this guy is pretending. He's not actually quite this incompetent, but he's pretending well, you can guess what he's pretending to do, right? Kind of typical day for a graduate student. And this child, he's not going to copy this guy. He's not going to do the stupid thing that this guy was doing. He's actually going to do something a lot smarter. So he didn't just copy the experimenter's behavior. He actually inferred the experimenter's intention and then took the actions that were better at satisfying that intention. And we can do that with robots too. So this is an example of inverse reinforcement learning with a robotic system. So here the demonstration, it's a kinesthetic demonstration, so the user is actually directly guiding the robot's arm. But the robot is not just going to copy these demonstrations blindly. The robot is actually going to watch the demonstrations and infer what is the intention of the demonstrator. And then it can figure out that the intention is really to like pour from the orange cup into the yellow cup, so that when the yellow cup is placed at new locations, the robot can then figure out a behavior that will pour, in this case, the almonds from the orange cup into the yellow cup at new positions, sometimes a little precariously. Okay, let's talk a little bit about prediction. So far, when we talked about reinforcement learning, we talked about reinforcement learning as the problem of learning a pattern of behavior, a policy, or a controller. Prediction also plays a really important role in decision-making and control. Certainly in biological systems, the idea that the prediction is a really integral part of sensory motor control is something that has been around for a really long time, and it's an idea that many people subscribe to. You can imagine using prediction as a tool for real-world control, and I'm going to show you a few examples of this. So here's an example where a robot learned how to predict what will happen in the world by interacting with objects. So it was kind of executing these random behaviors, pushing things around on a table. And then after doing this, this is actually some work by Frederick Ebert, who's actually the head TA in this class this semester. What Frederick did is he trained a model not to do anything in particular, but just to predict what will happen next. So what you're seeing in these two rows are different predictions from the same starting image, but for different actions. So this model is literally predicting what will the robot see if it does different things. So Over here, it's saying, well, if I move up, if I move left, if I move right, etc., what will the world look like? And the predictions are, they're not perfect predictions. They're kind of blurry. They're a little bit uncertain, but they give you a rough idea of what might happen next. So it figures out here that if it moves the arm to the right, then it might be able to slide this object over here to the right as well. So then this predictive model can be used to figure out how to bring about some desired goals. So maybe we're going to tell the robot now, whatever object is located over here under this red dot, move it over here to this green dot. And we'll ask the robot to try to imagine multiple possible outcomes, basically pick different action sequences, run them through the predictive model, see what the model predicts, and pick the action sequence for which the predictive model predicts the outcome that best aligns with our desired goal. So here's the best prediction the robot came up with. It says, well, maybe if I reach out for the stapler, then I can kind of slide it a little to the right. And if we then run those actions, then we'll see that the robot actually does something somewhat similar. Far from perfect, but kind of has the right high-level idea. And you can take this concept and you can take it a little bit further. You could, for example, imagine using predictive models to figure out how to use tools. So the nice thing with model-based RL is that you can plan for new behaviors that were not necessarily the behaviors of the pulse that you trained for. So you could, for example, say, well, maybe if I want to slide these two objects down, how do I do that? And the robot might come up with a strategy like this. Let's pick up the sponge and use the sponge to slide these things. If I want to slide this object up, maybe the robot figures out that it can reach out for that tool, grab the tool, and use the tool to slide things around. And if you left a bunch of junk on the table, it's going to look at this thing and say, well, I don't, these pieces of paper, I'm not sure how to move them, but maybe this thing over here can act as a tool, so I can pick up the water bottle and use the water bottle to slide the garbage or something like that. And you can do this in other settings too. For example, you could play games using predictive models. So this is some work that actually came out this year. This is a predictive model that was trained to play Atari games. And what you're seeing here in the middle is the real Atari game images. So this is actually the real game. And what you're seeing on the left are the predicted Atari images for the same action sequence. And on the right is the difference. So they're not exactly the same. The game has some complicated stuff. Sometimes one enemy comes out, sometimes three enemies come out, but it kind of gets the right general idea. So you can see that it's essentially a learned version of the game. But of course, predictive models don't always work perfectly. So sometimes they go a little bit wrong, and we can see some issues. So here's a boxing game. And this is an earlier version of the same system as over here. And in this boxing game, it actually made a little mistake. It kind of unintentionally made the game a lot harder than it should be by making a second boxer come out behind the, the middle boxer. And obviously, that makes it much harder than the game really is. So in the real game, there's always two boxers. But here, I decided that maybe adding a third boxer will make it more exciting. All right. So that's maybe a high-level kind of whirlwind tour through some of the things that we'll discuss in this class, and we'll of course cover inverse RL and predictive models and core RL algorithms in much more detail. But for the last portion of today's class, I want to sort of step back a little bit and discuss at a much higher level one possible motivation for studying deep RL, and this is really the motivation that resonates the most with me, and maybe this is something that you guys will be a bit interested in too. Not the only reason to study deep RL, but something that I personally find really interesting. And that's coming back to that question that I posed at the beginning of the lecture: how do we build intelligent machines? If I were to actually ask you how do you build an intelligent machine, I say, okay, write a design document for me. How would you actually build an intelligent machine? Where would you start? Well, one way you could think about it is you could say, well, when I learned about engineering complicated systems, they taught me a few things. One of the things they taught me is break it up into a bunch of parts and see if you can build the individual parts, kind of unit test them, and then wire them together. And that's a very reasonable way to think about engineering complex systems. And that's in fact how people approach the question of building intelligent machines for the longest time. They thought, well, you can look at the brain. The brain consists of parts. Maybe in the olden days we had kind of a naive view of what those parts are. Maybe those parts had to do with our virtues and vices. Perhaps in the modern day we have a slightly less naive view, or at least we like to think that way. But either way, there's parts. Those parts have functions. We can implement those functions in a computer. Maybe we program in the visual cortex and we program in a cerebellum and stuff like that, and then we kind of glue them all together, and hopefully we'll get something that emulates the behavior of the brain. And this is the way that people thought about artificial intelligence for the longest time, since the 1950s, and it turns out to be really, really hard to do this. It's really hard to do this for basically the two obvious reasons. One is that each of these parts are themselves quite complicated, and the second one is that when you go to wire these parts together, they typically don't like working together very effectively because of those abstractions I mentioned before. So when, the core assumption in a modular software system is that you can choose the right abstractions to use as interfaces between those modules, and that turns out to be very difficult for systems that have to interact with complex natural environments. So what else could we do? Well, we could imagine that maybe instead of having to implement each of those parts ourselves, we can use learning as the basis for intelligence. Why might we think that learning is a good basis for intelligence? Well, here's maybe a very hand-wavy argument. You can agree with this or disagree, but I'll just describe this briefly. There are some things that we can all do very well, like walking. So you might reasonably assume that, well, maybe we just sort of come out when we're born, we're like able to walk right away. But there are also some things that we can only learn, like driving a car, right? So there are clearly behaviors that, whether or not we argue about whether there's anything built in, whether recognizing faces or walking or whatever are things that people just do naturally, there are clearly some things that people do not do naturally that we have to acquire from experience. And not only are there some things that we have to acquire from experience, but those things that we can acquire from experience are highly varied and they're very difficult. You can learn some pretty complicated stuff that is clearly not kind of programmed into you by evolution. So therefore, our learning mechanisms are likely powerful enough to do everything that we associate with intelligence because whatever might be built in or not, we can learn some, there's clearly things we can learn, and the things that we can learn are very complicated. So if we for a minute accept this notion that our learning mechanisms are powerful enough to acquire all of the kind of complicated behaviors that we associate with intelligence, that leads to a different idea about how to build an intelligent machine. Instead of implementing the functionality of each of those parts, what if we implement learning algorithms that can acquire the functionality of those parts? That's maybe a start. Maybe we could just program in a different, a learning algorithm for the visual cortex, a learning algorithm for the motor cortex, and have them all acquire the functionality of each of those parts. But we might find ourselves having to implement many different learning algorithms in that case, and it might be very difficult to really bridge that gap having to do with wiring different modules. So maybe we can take another leap and suppose that maybe there's a single learning algorithm that can do all of this. Maybe you don't need a different learning algorithm for perception and a different learning algorithm for behavior. Maybe just one algorithm will suffice. Could this be the case? So maybe we could imagine a learning algorithm for each module, but we could entertain the notion that we have one algorithm for everything. Is there any evidence that this could be the case? Well, there is a little bit of evidence. It's somewhat circumstantial evidence. You could, for example, build an electrode array attached to a camera. You can put that electrode array on your tongue, and then you can try to use your tongue to perceive things through a camera. People have actually done this experiment, and it kind of works. You don't have great visual acuity that way because your tongue is not quite as sensitive as your eye is, but you can repurpose other sensory organs to do different things. And in fact, if you do this surgically, you can get a slightly more compelling bit of evidence. This experiment was done in ferrets, not in humans, contrary to what the picture might suggest. But there's a very well-known experiment where the experimenters actually took the optic nerve for a ferret, surgically decoupled it from the visual cortex, and then connected it to the auditory cortex of the ferret's brain. Now, initially, the ferret was pretty unhappy about this, but after a while, it could actually regain some degree of visual acuity, essentially learning to see using its auditory cortex. Now, that's actually quite remarkable if we think about it, because processing visual information is extremely complicated. So the fact that the ferret's auditory cortex could actually adapt to process information from the optic nerve suggests that whatever learning process the auditory cortex had at least something in common with the learning processes going on in the visual cortex. So if we do entertain the notion that a single algorithm can acquire the functionality of all of these different parts of the brain, then we could ask, well, what must this single algorithm be able to do? Well, one thing it needs to be able to do is it needs to be able to interpret rich sensory inputs. So if you have this one algorithm that can learn to see, and it can learn to hear, and it can learn to touch, it needs to be able to process high-dimensional observations, things like image pixels and waveforms and so on. Do we know of anything that can do this? Well, yes, we know that deep neural network models are actually remarkably well suited for the task. But there's another thing it needs to be able to do. It needs to be able to choose complex actions. It needs to be able to actually interpret those sensory signals, run them through some complicated processing, and come out with a solution to a problem that requires rational behavior. And reinforcement learning is what gives us the mathematical formalism for this. So why deep RL? Well, because the deep part can allow us to process complex observations and also compute really complex functions, and the RL part can allow us to choose complex actions. That doesn't mean that the brain does deep RL, but it might suggest that what deep RL does might accomplish similar ends. So let's look a little bit at some of the evidence. And I will say right now that the evidence is circumstantial, but people have actually studied some of these questions. For example, one of the things that people have studied is the degree to which the representations learned by deep learning algorithms resemble the representations that are observed experimentally in brains of humans and animals. So in this paper by Andrew Sachs, what the researchers did is they actually studied different sensory modalities. They studied vision, audition, and touch. And for these three modalities, they recorded data, trained representations with deep neural networks on that data, and then compared the statistics of the learned features to the statistics of features observed in primary sensory cortices. I believe in this case they were all, okay, so the touch was in monkeys, this was in cats. I don't remember what the audition was, but kind of different mammals. And what they observed is that the statistics of the learned features are actually remarkably similar between the sensory cortices of animals and the representations learned by deep neural networks. So for a quick kind of high-level overview of some of these experiments, for the visual features, what they did is they used these kind of canonical stimuli that have oriented edges, which are often used to study the kind of features that neural networks have and the kind of responses that brains have. So you can kind of see which neurons fire when you expose the animal to different simple oriented stimuli like this. For touch, they had kind of an interesting experiment. The animal data came from a monkey whose hand was placed on a rotating drum with some indentations on it. So because you know what indentations the drum has, you can record from the monkey's brain, and whatever you record is the corresponding neuronal signal corresponding to the pattern of indentations on the drum. And then for the neural network, what they did is they actually got people to put on this blue glove and play with an object that had some white powder on it. Then they took a picture of the glove, so the white powder reflects the bits that the people touched, and then they used those images to train a deep neural network to essentially extract what they called tactile features. So, okay, somewhat circumstantial evidence. What does it suggest? Well, it doesn't really suggest that neural networks do the same thing that brains do. What it suggests is that the features that are acquired by these models resemble the features that brains pay attention to. That could imply a few different things. One of the things it could imply is that if you take a powerful enough function approximator and expose it to enough data, you basically get the right representation of that data, and perhaps both the brains and the neural networks come up with the right representation. Reinforcement learning. This is actually an even more widely studied topic. In fact, reinforcement learning was initially proposed as a model for animal learning and only later became a useful tool in computer science to get AI systems to behave rationally. So reinforcement learning in the brain has been studied extensively, and there's quite a bit of interesting evidence to support that part of what brains do looks like reinforcement learning. So, for example, one of the things that people have observed is that percepts that anticipate reward become associated with similar firing patterns as the reward itself. So if the monkey receives the juice, it'll have a particular kind of pattern of neuron activations when it receives the juice. If the juice always follows the monkey seeing a particular pattern on a screen, then it will have that same response to seeing the pattern on the screen. Now that kind of seems a little obvious at first, but when we study temporal difference learning later on, we'll actually see that this is exactly what you would expect from a system that is doing temporal difference learning. There's been experiments that study how the basal ganglia appears to behave like the reward system for this reinforcement learning process, and how model-free RL-like adaptation is often a good fit for experimental data of animal adaptation. But not always. And there's also quite a bit of contradictory evidence that says that whatever animals do, it sort of goes beyond just the naive models of reinforcement learning that we have. So what can deep learning and RL do well now? Like basically, what are the things that seem to be going right? Well, RL can acquire a high degree of proficiency in domains governed by simple and known rules, domains like the game of Go or an Atari game where you can basically play the game as many times as you want, you know how the world works, and you're just going to use that to distill it into a pattern of behavior. RL can learn simple skills with raw sensory inputs given enough experience, for example, robotic grasping skills or some basic robotic manipulation skills. And deep learning models can do a pretty good job of imitating human-provided expert behavior, even in more complex kind of open-world environments, like the driving scene that I showed before. But there are some things that have proven very challenging and some things that are still kind of major gaps in our understanding and also major gaps between the capabilities of our machines and the capabilities of biological intelligence. For example, humans can not only learn from experience, humans can also learn very, very quickly. This is a schematic of an experimental setup on motor control where the person is supposed to move this lever to a particular location and the lever introduces a perturbation to push them out of the way. People can adapt to that perturbation extremely quickly in just a few trials. No reinforcement learning system can do that. So clearly there's something else going on. Deep RL methods usually require quite a bit of experience to learn effectively. Humans are also really, really good at reusing past knowledge. So we very rarely actually learn things from scratch. We actually use, a lifetime's worth of experience to learn things much more efficiently. Transfer learning in deep RL is still a very open problem. We'll talk about that in this class, but obviously there's still a really long way to go. It's often not clear in reinforcement learning systems what the reward function should be, and we don't fully understand how that works for biological intelligence. And it's also not clear what the role of prediction should be. So it seems like prediction and understanding the world, learning how physics works, how other agents in the world behave, that's a big part of what biological intelligence does. And it's still unclear whether that's a totally separate piece of the puzzle than model-free RL or whether those pieces should fit together in some more profound way. So there are many open challenges, and hopefully the material we'll cover in this course will help us to understand at least how to get started on some of those challenges. Okay, but at a high level, the thing that I really want to conclude with is the following idea that perhaps contrary to the obvious way of approaching AI in terms of thinking of it as a system of interconnected modules, deep reinforcement learning offers us a way to think about AI in kind of a much simpler way potentially, as formalizing a single algorithm, applying that algorithm together with very high capacity models, and then using experience to basically learn complex intelligent behavior. I mentioned before that many of the ideas underlying deep reinforcement learning have really been around for a while. And this idea is no exception. In fact, the idea that a learning machine, a universal learning machine, can acquire behaviors that resemble biological intelligence is very, very old as computing itself. And this is a quote that I like very much on that topic. Instead of trying to produce a program to simulate the adult mind, why not rather try to produce one which simulates the child's? If this were then subjected to an appropriate course of education, one would obtain the adult brain. Now, this is a quote from Alan Turing. That's it for today's lecture. I'll see you all next week when we talk about our first technical topic, which will be imitation learning, and we'll also release the first homework assignment then. Hello.